right, so welcome to the dynamics course. What I want to do here at the very start here is just talk about and have a brief introduction about, well, me. I'm your instructor. My name is Professor Scott Reckinger, and I hope to be interacting with you quite a bit throughout this process. And also introduce you to the course of dynamics, in particular where it belongs, how we place it inside of the study of, well, of engineering mechanics, our study of physics, our study of just looking at the real world, looking at reality, using the laws that describe nature to for engineering purposes, right? So to better society and do innovative, build innovative technologies with it. I also want to introduce you a little bit to the course structure in terms of these lectures. But in this short intro part here at the beginning, this is one way you'll be seeing lecture and example problems in the videos to come, but a limited way. In fact, the most of the time you'll just see me working through like what looks like a document camera, where it's just my writing that you're going to see, and that's just a more efficient way to communicate some of the more complicated concepts. But I think this is a really engaging environment that I'm going to try to use as much as possible, and it allows me to interact with you one-on-one, even though we are separated by both distance and time, right? Meaning you're not watching me live, and we might not even be currently in the same country. Well, so the main idea with this class, and I'll have more to say with this at the further parts of this video, is this is not the ideal way to learn in many ways, right? The pace of the class is not ideal. The fact that we aren't in the same room during the lectures is not ideal. But what we want to do is take advantage of what is the benefit of it, right? You're going to be watching videos, so you can pause the videos when you need to slow down. You can rewind, go back to concepts, right? It's not just one shot at taking notes. Take advantage of that, right? Take less advantage of the fast forward capability. I hope you're taking notes the whole time and following all of anything I write. I think it's important. But hopefully taking advantage of the technology in terms of going at the pace that you need, while understanding that the course is at very fast pace. So having said that little motivation here, what is dynamics? So what I'm going to do now is put dynamics in its place in our study of physics. Okay, and so we can get rid of my name. I'll replace my name with physics, right? Isn't that appropriate? Wouldn't that be great? Okay, so all right, so physics, just from its name, we are just trying to study and understand better the nature around us. Okay? So this is just an introduction to dynamics. I hope you're taking notes on this, but now going forward, note that when I write something down, that's something that I think that is important enough to write down, so it should be something that you're taking down. And treat this like class time, right? Treat it like I'm in person, right? But again, take advantage of the fact that, well, you can go back and revisit topics. Okay. So introduction here in this first video. Knowledge is physics is knowledge of nature, having knowledge of nature. What we want to do more specifically on how it pertains to dynamics is study. It's the study of matter, and then matter's motion, right? So if that matter starts to move, both through space and time. Okay, and more specifically, what causes that motion? Okay, so the forces involved, the things that push bodies around, the thing that push matter, and the energy associated with it. Okay, and the energy forces that cause that motion, changes in energy. Okay. Okay, so this is the main idea. Now let me do something. I'm going to put dynamics in its place in our study of physics. So here's physics and our study of it. Let me now make a little diagram that puts dynamics in its place. So what I've done here now is taken our knowledge, our study of nature to get better understanding of it and what we can do with it, and broken it down into how the different fields of physics, right? Where the one we're focused on is engineering mechanics, right? It's one way to describe nature, right? We can also go to temperature and heat more focused fields through thermodynamics, focused on electric and magnetism effects, many others, right? Maybe there's planetary description of planetary motions that requires some combination. In fact, there's lots of combinations. There's optics, right? Optics deals with electromagnetism, but does that belong in its own field? So a lot of interplay between these main fields of physics. Well, this is just one way to categorize it, which is engineering mechanics, which is where we're in, right? And again, this is within the realm. In fact, it's at its nature studying matter, the motion of matter as it moves through this thing we call the space-time, field, both space and time changing. And then what are the forces that involve moving that matter, and how does the energy of that matter change through time and space? Within engineering mechanics, we study statics and we study dynamics. Now, statics is the study of when acceleration is zero, so when bodies don't move or don't change their motion through time. That's going to be the scenario from Newton's second law where the forces on an object sum up to zero. Okay? What we do in dynamics is combine, well, we don't basically say those two things are separate or they're zero independently, right? In that they actually are equal to one another, right? So if there is a sum of forces not equal to zero, it equals its mass times its acceleration. I mean, this is where we're going to be talking about this all semester long. For the next, 40 lectures, whatever it is, this is going to be at the heart. And we'll be messing with this. We'll be dotting this with position vectors. We'll be integrating it in time to get to different forces and energy relationships. This is at the heart. When you apply force to an object, it causes it to move through space. Okay? Now we break down dynamics into two general places of study, right? Which is kinematics and kinetics, and that's all built up into the built into the description of physics I have up in here, right? Which is, you see, we have motion and then the forces and energy that cause it. Kinematics is a pure description of motion. Okay, so this is the study of the geometry of motion without worrying or without studying, so independent of the forces causing it. Okay? And I'm going to make these boxes fit once I'm done writing. Kinetics, on the other hand, is the other part, right? Is now, well, let's consider the forces. So we often study kinematics first and then jump into kinetics, and that's what we'll do here in dynamics. So this is the study of forces that cause the motion, the change in motion. And we're going to study this in three different methods, right? Three basically general approaches, analysis techniques, which is to look at the relationship between force, mass, and acceleration coming straight out of Newton's second law, force equals mass times acceleration. We will do something to turn that equation into something where we can look at work done to a system and the energy and the components of energy in that system. And then finally, we can do something to integrate this through time to get a change in momentum and the impulse involved in acting on a system. Momentum. Okay, so those are the basic analysis techniques of the class. Okay, and so now, and this is like the study of dynamics. Who cares about the class, right? These are the components we have to talk about in order to describe motion and do that through its connection with the forces that cause it. Okay. All right. So if we were then to add to here a course outline, an outline of the things we're going to study, it's not necessarily this and then this. Okay, we can be more specific and get us all on the same page here. So in terms of a course outline, on my screen, that one's off the page, or that one's off the screen. Okay, we are going to basically study both of these. Okay, all right, so we have kinematics and kinetics for, so study kinematics and kinetics for, well, part one of the course, first, like, big part of the course is for particles. Okay, and this is what we mean by a particle, is where something has mass, but we accumulate all that mass at a point. All right, so there's no distribution of that mass. It's just all collected at a point. Okay, we'll then study kinematics and kinetics in part two for 2D rigid bodies. So what we mean by 2D is that the motion can be collapsed into about one plane or on one plane. So what we mean by rigid, non-deformable, so they can't change, no changing shape, mass distribution. Okay. And planar motion, we call it. Okay. And then part three of the class is going to be just the last unit, which is kinematics and kinetics for 3D, so full 3D motion of rigid bodies. Full 3D motion. Okay. So before we move on from this introduction to the course, let's put in where we're going to study these things. So we're going to start here, kinematics. This is going to be chapters 13 in the book, and then 17 in the book, and then section 20.1. And what I mean by this is, well, this is the part 1 kinematics. This is part 2's kinematics for 2D motion, and this is where we'll see part 3 kinematics. All right, just describing motion without forces involved. You see how we start with kinematics of particles, and then we'll do, then we're going to jump over to here. So the chapters here for each of these study will make a column over here. The chapters we study force, mass, acceleration is going to be 14, and then 18, and then section 20.2. The section we study work energy is going to be 15 and 19, and then we don't do it for 3D motion. And then 16 and 19 is our impulse momentum, and we don't do it for 3D. Okay, so this is again part 1 in this column, part 2 in that column, and part 3 in that column. So mass at a point, so particles, 2D motion, 3D rigid body motion. Okay, so I hope that helps see where we go, and if you were to watch this video again at the end of the class, you know, you can now look back on this and say, oh, I remember now how all of this is what we studied. Okay, so what you see next is, now we're going to go to, you're not going to see me until the next time, in the next example problem when this is the format I chose for doing that example problem. Instead, you'll see me working through the introduction in chapter 12, making sure we're all on the same page in terms of the prerequisite content that we should come into the class being familiar with. Okay, and that'll wrap up this lecture, and then we'll get into chapter 13 in the next video. Okay? Okay, so let's see now. Let's talk about what content is in chapter 12, which is the first chapter here. In the book, and it's really a review chapter. It's supposed to get us all on the same, on the same page. Not meant to scare anyone away, right? It's just if there's areas that you don't have as much experience with, maybe just that's what you focus on, right? There's not even any homework problems that we have assigned. Right? You can work through some of the problems in this section which is a good place to get caught up if you feel like you need to. Now, and I know that like a lot of these things we can figure out as we go along the way. It's just in the pace of this class, we might not have the luxury of that happening, right? I think the other goal of like what I want to do here is to show how these videos might be formatted, or what you expect to see. So right, so we're going to use that like Lightboard technology in a limited fashion, right? I mean, I think it's a great technology, but it's a bit easier for me to be recording these types of videos. And so this is like the main way you'll be seeing the content in the class, right? It'll be in more like a document camera, right? So where it's just me writing, and you won't be able to see me other than my hand here. And I'll try, we have a lot of right hand rules, so I have be able to do that here. But anything beyond, but most of it'll be just be me writing. Now, in some of the videos, I'll have some pre-written content here, and in other ones, I'll just be writing most of it. I mean, this will be limited, what's already here. Oftentimes, it'll just be like the review material from like the previous section, and then anything anything new, I'll be writing. And so it's really a message to you to take notes along with me, just like a regular lecture. But again, take advantage, and I will be thinking of this to take advantage of what we can with this. Right. So in many ways, it's not ideal in that like the pace of the class is really difficult for an engineering mechanics class. Really difficult to have these concepts become, build intuition based on them. But also we'll take advantage of the video format. So if you can pause and go over the material that's pause, rewind, which is not available in a regular lecture, right? For when the material gets complicated. You can also go to ×2 speed if you ever feel that there's you got kind of the examples down, or let's say even like you want to just have the derivation written out for one of the theory parts of the class, and you would rather just wait till have it on the screen, and then you can take notes on it. But I should say, right, my huge recommendation is watch all the videos, watch all of them, right? Commit to this class the time it deserves. In addition to that, take the notes as if you were in class, right? As if this is a lecture. There's research out there that show just by writing it down once, there's better retention of the material. We're going to need to rely on that retention here in this fast-paced class, and so I can't stress enough how important it is to treat this like a regular class. Take all the notes, which is why I'm writing it. I have notes sitting right next to me when I'm working through these things. I could just show you the notes like I do here. I don't think it's as important for the stuff that I have already here, because it's usually review material, or not that important for you to write it down, right? Here's just kind of a list of ideas you'll find in chapter 12, so if you need to go do it, right? Still write it down, right? But pause the video and write it down. But really, when it comes to the really, really important stuff, I'm going to be writing it. Take notes with me, just like you would in class. Pause when you need to, rewind when you need to, fast forward in a limited way, but you can take advantage of that. What I mean by fast forward is watch it in double speed or 1.5 speed or something like that, okay? So, to give a little feel for how this is going to go, there might be some material here. I'll talk through it, and then we'll write some more stuff, which is just like what I'm going to do here. This is chapter 12. It's really a chapter for introduction to dynamics and really getting us all, getting the tools up to where they need to be able to succeed with the, chapter 13 material and onward. So in chapter 12, there'll be some general problem-solving strategies, right? This is breaking a complicated down into its individual components, being organized with your work, showing all your steps, advice like that. The next bit is talking about significant digits. My recommendation here, right, there's some technicalities here about like when values are given to you in a problem statement, there's actually information there into how significant those values are. I mean, how much resolution there is on the numbers. That's important, right? But maybe we, learn that, have that as a learning experience throughout our education. What I basically want to say here is, work through problems, keep as many digits as possible during your calculations, right? So have a calculator ongoing. I use a software program to do any of my calculations, and that keeps as many digits as the computer can store. And then when I go to report an answer, 3 to 4 digits. And this becomes important when I'm working through a problem and I'm keeping like 8, 16 digits. and then I come to one of the answers, right? And then I have to use that answer in the next step. I don't want to be using my reported 3-digit response to part A when I go into answering part B. I want to use the full resolution I have to that, and then when I get to the end, report it out to 3 to 4 digits. Okay, is that, that's how I see significant digits, at least in the context of this class. The worst thing you can do is to report something that is 0.0005 as 0.0005, because there was probably more digits beyond that, right? 5 is just the first digit that's important, right? So 0.00514332, right, would be a better answer. There's also a discussion here in chapter 12 of space and time, right? I think that's intuitive, beings that live in the universe of space and time. We kind of have a feel for it. But what we mean by this, right, which is going to be absolutely vital from the get-go here, is this idea of how position, velocity, and acceleration relate. Okay, here's the first time you're seeing me write as we go here. And so that's going to be absolutely vital, just these general relationships, basically, that if you know your position and then it's changed in position over time as time changes, so that as time, so I guess the space gives us this as the spatial changes. Space is position, and then as we move forward in time, if our position changes, then that's our velocity. So it's really the time derivative of position gives us velocity, the time derivative of velocity gives us is acceleration. And hey, if we just understand that, we're ready to jump off into kinematics in the next lecture. Okay, the other aspect of this that I want to mention right now is all of these in general are vector quantities. So when we get into vector mathematics, that's going to be an important aspect here. Okay, these are vector quantities, and that means that we need to be comfortable also from day one and get ready to do vector addition. We need to do vector dot products. We need to do vector cross products. And with the vector cross products, applying the right-hand rule. When we get to cross products, and if any of those aren't familiar or they need review, now is the time to go review them, because they're going to show up week 1, just really day 1 here for the format of this class. They're going to show up early in this class and then be consistent throughout. So this is vector algebra, even a little bit into vector calculus, but not too complicated on that. Then there's a discussion in chapter 12 of units, basically SI units, so meters, kilograms, the ones I prefer, versus U.S. customary units, the ones that have just in our country, the ones that we've traditionally have been the ones we use, are also used in this book and in this class. And then conversions, not just between the two unit systems, but conversions between what a Newton is in terms of its kilograms, meters, and seconds. Okay, then there's a whole section on gravitational force and acceleration, and how we often use a constant gravitational acceleration, and why we do that from the universal gravitational law. Now, so go read about that. But yeah, again, day 1, we're going to be considering gravity as an important force and applying that constant acceleration there. The last, and we're going to actually take some notes here live as we go, is our Newton's laws of motion. And these are going to be the foundation of engineering mechanics. They are the foundation of engineering mechanics, and therefore dynamics being an important branch of engineering mechanics it's absolutely vital. What I mean is how many of your classes you have in engineering mechanics, right? That's from statics. Well, it starts in physics, and then we, physics 1 and 2 usually. Then we jump into statics, dynamics, some sort of mechanics of materials or strength of materials. There's fluid mechanics, thermodynamics, all of these different branches that relate to engineering mechanics. They're all, going to be governed by a few different principles, and just a handful. And one of the main ones in engineering mechanics is Newton's second law, force equals mass times acceleration. But first, let's start with Newton's first law. And I'm just going to write out the description here. What this says is that when the net force on a body or a particle whatever the object under consideration is, when that net force is 0, that can come from being no forces or that there are equal and opposite forces that cancel each other out. The law says that the velocity of that object, of that body, of that particle is constant. Not that it's 0, but it's constant. Okay, so this is the scenario where there is no acceleration. So if velocity is constant, then acceleration is 0. Okay, this is a statics. This is the main focus of statics. It's Newton's first law. Okay, and that is that some of the forces are 0. And you also had some of the moments are 0, and that's just, with a chosen coordinate system, a chosen origin, the rotational effects of any forces also cancel out. Okay. Okay. Then we get into Newton's second law, which is an extension of the first law, right? Basically, the first law is a generalization. So let's do ... sorry, the first law is a special case for the second law. The second law is a generalization. So ... Otherwise, if that's not true, if it's not true that the net force on a body is 0, so that means it's non-zero, as long as we have a constant mass, which we will be assuming all along here, if the mass is constant, then the sum of the forces, so that net force, equals, and these are all vector quantities, equals the mass of the body or the particle times its acceleration. Okay, and so we got acceleration, so here's the acceleration is now non-zero. We have a non-zero acceleration. Oops, slid off there for a second. This now is dynamics. This is where dynamics lives. All governed by force equals mass times acceleration, right? So before we had, well, if the left-hand side is 0, then the right-hand side is 0. Now neither of them are 0. And these make up our main branches of engineering mechanics. Main branches of engineering mechanics, namely statics and dynamics. Okay, and you should have taken a statics class, previously here. Okay, and then the third law, right, which we will see showing up again. Again, number 2 is going to be the main thing. I mean, all semester long, we're going to be using this. We're going to be dotting this with position vectors, with differential position vectors. We're going to be integrating this in time. We're going to do all sorts of crossing this with position vectors, all sorts of crazy things. It's all going to stem from right here, and I don't know how to make this important enough. This is the name of the game. This is the main law for this class. It all stems from that. And if you can leave here after our quick, rapid, high-paced study of dynamics, getting an intuitive feel for how powerful this statement is, that's all we're really looking for, okay? That's all that you really need to know as an engineer, right? Okay, and the third law, the forces exerted by two bodies or particles on each other are equal, so equal in magnitude, and opposite in direction. This is another important principle to talk about. Definitely when we get into collisions between two bodies, that's going to become vital. Now, this belongs in both branches, right? This third law. So I'll just sneak in here both. If we're kind of going to categorize them as statics or dynamics principles, this plays an important role in both statics and dynamics. So if in statics, if there's no acceleration, well, when you have like a support, you have a structural element being supported by a pin support, right? The force on the pin is the same as the force on the bar in that support, right? That's the statics principle. In dynamics, right, you got two particles in collision. When they're hitting each other, the force on one is equal to the force on the other, but in opposite direction. And so if you take the system of the two particles hitting each other, there's no net force on that system, right? So that's why we see both statics and dynamics principles being at play, or why Newton's third law makes statements about both statics and dynamics ideas. All right. Okay, so that kind of wraps up chapter 12 and gets us ready to jump into chapter 13, which is really the start of our study of dynamics. We're going to start with a look at kinematics of particles, where a particle is, we're collecting a mass all at a single point, and we're not really dealing with real objects, where we'll get to those bodies, really the objects and their mass distribution, about halfway through the class. Okay?